Hi, this is Mrs. Baisden, and in this screencast we're going to learn how to do empirical formulas. So when we talk about the formula of a compound, there's two different terms we can use. First one is the empirical formula. This is the smallest whole number ratio of all the atoms that are present. Then the other type of formula we can look at is something called a molecular formula, which tells you the actual composition of the molecules present. So the molecular formula gives you the actual number of each of the atoms present. Now you'll see that sometimes these two things can be the same. Sometimes the empirical formula will be different than the molecular formula. So what we're going to do is look at an example here. Our first one, and look at the difference between the empirical and the molecular. So if we look at our first one, we have C6H6. This is an organic substance called benzene. Okay, so here's our C6H6 that we're starting with. So what we want to look at is this is the molecular formula, what is the empirical formula? So we're going to look at this and see if it's possible to have a lower whole number ratio. So for this one, since we have 6 as the subscript for both of those, we know that that could be reduced, if you want to think of it that way, as CH. Okay, now one way to write the empirical formula is sometimes you will see it written like this, CH, and then in parentheses you'll see whatever number you divided everything by written on the outside like this. So you could give it either way, but when all we're asking for is the empirical formula, a lot of times it's just written like that. Okay, so now we're going to look at the next one. This one is C12H4Cl4O2. This is something called dioxin, which is a poison that can occur when they're producing other chemicals. So this is something that is very dangerous. So if we look at this, we can also reduce our subscripts here. So we can divide all of these by 2. So we would then have C6, H2, Cl2, O. And again, if you wanted to, you could write it this way, C6, H2, Cl2, O. And then we could put our 2 on the outside. So we can divide all of those by 2, and we end up with C6H2Cl2O. Now our last one, C6H16N, is a substance they use to make nylon. So if we look at this, our empirical formula is actually the same as our molecular formula because there's no number there. There's nothing we can reduce all of those by. So our answer to this one would just be the same formula, C6H16N. So this is a case where the molecular and the empirical formula end up being the same. Okay, so when we calculate an empirical formula, this is kind of the reverse of what we did in the last screencast when we learned how to do percent composition. So in this particular type of problem solving, what you will be given is the percent, either the mass in grams or the percent composition, and you'll have to work the other way and figure out what the formula is. So for those of you that like to see the steps ahead of time, these are the steps for doing this, and it's your choice whether or not you write these down. We're going to go through several examples here in a second. So the first thing you do is you need the mass or the percent of each element in grams. If you're given the percents, then you just assume 100 grams. So if it says it's 12% carbon, then you write down 12 grams of carbon. Then you convert the grams to moles. Then you divide all of those moles by the smallest number of moles to get the lowest whole number ratio. If you don't end up with whole numbers at that point, then sometimes you need to multiply to get everything to be a whole number. We'll do an example like that in a second. And then those numbers that you end up with are the subscripts of the formula. So just like always, the easiest way to learn how to do one of these is just to watch some examples. So our first example says, we know this compound only has carbon, hydrogen, and okay, so again, we know this compound only has carbon, hydrogen, and oxygen. It was determined that 0.205 grams of this compound was obtained from a reaction. Now, when you're doing these, there's going to be a lot of numbers in here, so you're really going to have to pay attention to which of these numbers you need and which of these numbers are just extra information. So that first number they give us is actually the total amount that they're starting with here. So the numbers that we need is we know that carbon, there was 0.0806 grams of carbon. There's 0.01353 grams of hydrogen, and 0.1074 grams of oxygen. So we're going to start this out very similar to what we did before. So I'm going to list what my elements are. So I know I have carbon, I know I have hydrogen, and I know I have oxygen. Next, I'm going to write down how much of each of these I have. So carbon, I have 0.0806 grams. For hydrogen, I have 0.01353 grams. And then for my last one, for oxygen, I have 0.1074 grams. Okay, so that's my first step. Now my next step, like I said a minute ago, is to now convert all of those to moles. So I'm going to use my molar mass from the periodic table so that all of these are now moles. So for carbon, 1 mole of carbon is 12.01 grams. And notice grams cancels out, which is what we want. We want to end up in moles. For hydrogen, 1 mole of hydrogen is 1.01 grams. And again, grams cancels. And then my last one, oxygen, 1 mole of oxygen is 16.00 grams. Okay, so now I'm going to go through and do my calculations here. So for carbon, I end up with 0.006711. Now at this point, what I would do is I would leave at least 4 sig figs at this step right here. I know we're only rounding to 2 sig figs over in that first step, but if we leave 4 sig figs at the second step, a lot of times this is going to make our life a lot easier when we do our final calculation. So that's how many moles of carbon we have. For hydrogen, I have 0.01340 moles. And then for oxygen, I have 0.006713 moles. And again, notice I left 4 sig figs for all of those. So now what I'm going to do is, like I said, divide all of these by the smallest number of moles because I need a smallest whole number ratio here. So this first one is my smallest. So I'm going to divide everything by 0.006711. So obviously for that first one I get 1. This one, 0.006711. For this I end up with 1.99, which I'm going to round to 2. So that's really, really close, so I can round that. And then this last one, 0.006711. That one will also round to 1. So these all round to nice whole numbers. So these then are my final coefficients. So the formula of this compound then is C1, which I don't need to write, H2O. So that's my empirical formula of this particular compound. Okay, so now we're going to try another one, maybe. Okay, so here's my next one. This one I have an oxide of aluminum that's formed by the reaction of 4.15 grams of aluminum with 3.692 grams of oxygen. So again, we want to know the empirical formula. Okay, so just like before, this one I only have aluminum and I have oxygen. So for aluminum, I have 4.151 grams. Oxygen, I have 3.692 grams. So then my first step is going to be to divide by my moles. So 1 mole, or multiply by my molar mass, or divide by my molar mass, I'm sorry. So aluminum, 1 mole is 26.98 grams. And again, we're setting it up this way so that grams cancel, so we end up in moles. And then for oxygen, we have 1 mole of O divided by 16.00 grams. Again, grams cancels out. Okay, so I end up with 0.1538 moles of aluminum and 0.2308 moles of oxygen. So then my next step is going to be to divide by the smallest. So in this case, Aluminum's my smallest, so I'm going to divide by 0.1538. That gives me 1. And then for this one, divide by the same thing. But this time I get 1.5. Okay, now this number here, if you don't end up with something 0.1 or something 0.9, then you have to multiply by some number to get a whole number. So 1.5, we know if we multiply that by 2, will give us 3, but whatever we do to one, we have to do to the other, so that means I also have to multiply this one by 3. So then we end up with our nice whole numbers. So aluminum's subscript is 2, so I end up with Al2, oxygen O3. And then that's my empirical formula. Okay, let's do one more. And this one I have labeled as a practice problem. So again, if you feel comfortable with these, go ahead and stop for a minute, try this, see how far you can get, and then come back and check it. Okay, this one you'll notice is set up a little bit differently. Instead of giving it in grams, it's given in percent. But like I said a minute ago, since they gave us percent, we're still going to assume we have 100 grams and make those grams. So carbon, I have 63.68 grams. Nitrogen, 12.38 grams. Hydrogen, 9.80 grams. Oxygen, 14.14 grams. Next up, convert everything to moles. So carbon, 1 mole, 12.01. Nitrogen, 1 mole, 14.01, and again, those numbers on the bottom are coming from the periodic table. Hydrogen, 1.01, oxygen, 16.00. Okay, so for carbon, I have 5.302 moles. Nitrogen, 0.8837 moles. Hydrogen, 9.703 moles, and again notice I'm keeping 4 sig figs at this step. Oxygen, 0.8838 moles. Okay, next up, now I'm looking for my lowest whole number ratio, so I'm going to multiply by the smallest, which is this one. So everything is going to divide by the smallest. 8837, that gives me 1. Divide this one by 0.8837. That's going to give me 5.99, which I can round to 6. Next one, 0.8837. That gives me 10.98, which I can round to 11. And my last one, 0.8837. This is going to give me 1. So these nice whole numbers don't need to multiply by anything. So these then end up being my coefficients. So my final formula is C6N1, which I don't need to write, H11O. So that's my empirical formula.